Welcome to section 6.1, adding and subtracting polynomial expressions and functions. So before we start looking at adding and subtracting our polynomials, we have to do some vocabulary words. And the first thing we're going to go over is a monomial. And a monomial is a variable or constant where the exponent of the variable is a positive integer. All right, so it's best to kind of use some examples for this. So first of all, it could be a constant. All right, so there's a monomial. It could be a variable, which is a letter. And the exponent of a variable has to be a positive integer, so something like 5, okay? And it could also get more complicated. It could be like negative 9y cubed z to the 4th, right? So we can even have more than one variable. So examples of things that would not be a monomial are things that would have, let's see, not positive integers. So let's say we had a variable x and we said it was like x to the negative 3rd, right? That's a negative integer. Or x to the 1/4 power. That's a rational expression. That's not an integer. So these are not considered monomials. We are not going to be working with those expressions in this chapter. And then if we take monomials and we add them all up, then it becomes a polynomial, and it's a sum of monomials. All right, so something like 5x cubed y minus 5 z to the 4th plus 1/2 x minus 0.1. Something like that, right? That's a polynomial. It follows all of our rules. Okay. Let's consider this polynomial 3x squared plus 5x minus 1. Each monomial is called a term. So they're each called terms. And in this case, we have 3 terms. This is in descending order by the exponent on the variable. So we call this standard form. Notice the x's go x, the degree is 2. And then the exponent on here is 1. And then no exponent here, so it's really like x to the 0. So the exponents go 2, 1, 0. So it's in descending order. We call that standard form. And some other things, when we talk about numbers and variables, the 5 on here is called the coefficient. The 5 is called the coefficient of the x. And then 3x squared is going to be important to us later on when we're factoring. This is the leading term. It's the highest exponent. It's the first term in standard form, so it's the leading term. Okay, so we talk about the degree of a term, and the degree of a term is the exponent on the variable. If there's more than one variable, it's the sum of the exponents on the variables. So in this last example, our leading term, the degree was 2, because that's the exponent on the variable. So we'll write that down. So 3x squared has degree 2. And then if we had a lot of variables, like let's say x to the 5th y z squared, that's all one term because there's no pluses or minuses separating it. It's all one big product, so it's all one term. This has degree, and we're going to add up the exponents on all the variables. So 5 plus 1, remember 1 is the invisible exponent, plus 2, it has degree 8. Okay, and then a couple other things I want to mention. Remember constants. So let's look at just the constant 7. This would be has degree. Let me give myself some more room. Has degree And it doesn't have any variables, but we're going to say it has degree 0 because we know that if we were to put a variable on the 7, we could write it as x to the 0 because x to the 0 is 1 and 7 times 1 is 7. So any constant has degree 0. And then if we're actually talking about the number 0, this one's tricky because we could write anything. We could write 0 times x to the 1,000th power because it's still going to be 0. So to eliminate that confusion, 0 has no degree. All right, so just some information to consider. And then the degree of the polynomial, that's our next definition. So we have degree of a single term. The degree of a polynomial is the largest degree of any term of the polynomial. So let's look at an example. Let's say we had the following. Let's say we wrote negative x cubed y plus 7xy to the 4th plus 5. And now what's the degree of the polynomial? Well, we would have to go and look at the degree of all the terms. So let's go term by term. So x cubed y, what's that degree? Well, 3 plus 1 is 4. So this has degree 4. What about our middle term? That has degree 5. And our constant term always has degree 0. So what's the degree of the polynomial? What's the biggest one? 5. So we would say this has degree 5. Okay, so we're going to be looking at specific degrees, and linear polynomials or linear functions have degree 2. Or I'm so sorry, it has degree 1. We know that. So that's like your 4x plus 9, for instance. All right, so degree 1 is our linear functions. Quadratic functions, we haven't really dealt with that so much, but that's 2 degrees. So something maybe like 3x squared plus x minus 1. All right, so quadratic function, I should also mention for these linear and quadratic functions, only one variable. So degree 2 for quadratic. Cubic, think 3, so maybe like 4x cubed minus x plus 1, for instance. The highest degree is 3, so this is a cubic function. All right, so we have some special names for 3 of them. And then degree 4, we don't really have a special name for that. Okay, so to add and subtract polynomials, we combine like terms. So now we're doing what this section is called after we got through all of our definitions. And we've talked about like terms before. Like terms are either constants or variables that have the same exponents. So everything is exactly the same. So let's take a look at this example, 6x cubed plus 4x cubed. We have a variable x, and it's raised to the same power. So these two terms we see are like terms. Same variable, same power. Same variable, same power. Same. So how we combine like terms is we focus on the coefficients. We're going to focus on the 6 and the 4. So the short end of it, it's going to be 6 plus 4 is 10. But why it works is kind of like reverse distribution. We have this common x cubed, and we know we can distribute one way. We can also distribute the other way. So we're going to pull out that x cubed, and we're left with just 6 plus 4. Now notice if we were to redistribute the x cubed, one copy would go to 4 and one copy would go to 6. So we're not doing anything illegal. Everything is exactly the same. But now we can really clearly see why when we combine like terms, we do the math on the coefficients. And it's because of reverse distribution. So 6 plus 4 is 10. It's 10x cubed. Okay, so let's practice adding the polynomials. So we are going to focus on the like terms. So our polynomials are the ones in parentheses. So here's a polynomial, and then we're going to add it to our other polynomial. And it looks like we have a squared as a like term. So when we're adding, and there's no number in front of the parentheses, so when we're adding and there's no number in front of our parentheses, like in this case, the parentheses just kind of disappear. And we can just focus on combining like terms. So the a squared, we're going to do just the 8 plus 3. And I'll write out every single step right now. You guys won't be doing this in your homework. You'll just write 11 a squared. But just because this is our first time really talking about it, I'm going to write out every step. And then we have the AB like term. And we're going to be adding the coefficients -7 plus 4. And then our last like term is the b squared. And we're going to be doing the operation on the coefficients. All right, so 2 plus a -7. So our final answer is 11a squared minus 3ab minus 5b squared. All right, because 2 plus -7 is -5. All right, and we know we're done when we're simplified completely, no parentheses, no uncombined like terms. When we subtract polynomials, like in this next example, so again, here's our first polynomial minus our second polynomial. Before we do anything, we have a minus in front of the parentheses. That's something we have to clean up first. So we can do it in a couple different ways. Some students like to think of minusing each term in the polynomial. Some people like to think as distributing a -1, because that's really what's happening. So distributing a -1 to each term. And then some people just like to change all the signs inside the polynomial, inside the parentheses. However you slice it, I recommend rewriting it. And we should all be getting this next step, whether we're thinking of subtracting all the terms inside the parentheses, or we're distributing a -1 to all the terms inside the parentheses, or we're just switching all the signs inside the parentheses. Okay, we should all end up with this. And now we're ready to go. We're ready to combine our like terms. Okay, so I see an a cubed b. A cubed b. Do we have any other a cubed b's? No, 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 no. All right, so a cubed b is just going to hang out by itself. Nothing to combine. Next we have the 5, or a squared b. So do we see another a squared b? No, we don't. I hope we have some work to do here. All right, let's look at the ab cubed. Do we have another ab cubed? There's our ab cubed. No? Oh, there's an ab cubed. Okay, so I'm going to start underlining so I don't count a term twice or forget it. So this is a 1. Invisible coefficient is 1. ab cubed plus 7 ab cubed. So 1 plus 7 is 8. ab cubed. All right, do we have another 5a squared b squared? No. So there you go. And then negative b cubed, we don't have any friends with that either. All right, so there's our final answer. All we did was distribute the negative sign, and then we could only combine one like term. Everything else was unique. Okay, so a couple other things we're going to be doing this section. We're going to be working with quadratic functions. Quadratic is degree 2. And we're going to be plugging in values into our quadratic functions. So let's take a look at this next example. We have a function. It's in one variable, x, and our highest degree is 2. So this is a degree 2 function. This is a quadratic function. And you can write that out just so you get used to your notation. Quadratic. And we're going to find f of negative 4. So we're going to plug in negative 4. So wherever we see an x, we're going to replace it with negative 4. And we're plugging in a negative number, which is always kind of tricky, so parentheses are going to be important. So sometimes when I'm working with negative numbers, I'll just do parentheses first wherever I see an x, and then I'll come back and I'll fill in the input. All right, in this case, our input is negative 4. So negative 2x squared becomes negative 2 times negative 4 squared. Negative 5x becomes negative 5 times negative 4, and then plus 3. Okay, so let's simplify this. Again, we'll do it carefully since there's lots of negative numbers. So exponents first. So negative 4 squared, well, the base is all of negative 4. So negative 4 times negative 4 is positive 16. Next, negative 5 times negative 4. Two negatives in a product make a positive. And then we have plus 3. All right, last thing we have to do before our addition is multiplication. Negative 2 times 16 is negative 32. Finally, in PEMDAS, we do our addition and subtraction at the same time, left to right. Negative 32 plus 20 is negative 12, plus 3 is negative 9. So f of negative 4 is negative 9. Okay, so you guys will see some examples in your homework where you're evaluating quadratic and cubic functions. Using that function notation, when our polynomials are in one variable, like just x, for instance, they're functions. So we can do the same adding and subtracting, but we're going to use function notation. So for instance, these are our two definitions we're going to use. If we see something like this is what we're defining, f plus g, and f minus g is our new thing. And essentially this is what it is. We're just going to be adding together our functions. But it's going to make a new function. So let's look at an example. We have our function f and our function g. And we're going to find f plus g. So just as before, it's going to be one function in parentheses plus another function in parentheses. And then with addition, we don't have to worry so much because when there's nothing in front of our parentheses and we're adding everything, the parentheses just disappear. So all we're going to focus on is combining like terms. So 8x squared plus 3x squared. And then the x, negative 7x plus 4x. And then finally 2 minus 7. All right, and then let me write the correct notation. This would be considered a new function, f plus g of x. That's our new function. All right, so let's go ahead and push pause, and you guys can do the next function. And then once you have it, go ahead and evaluate it at 2. All right, let's check those answers. So you subtracted f minus g. You distributed the minus sign, or you subtracted all the terms. And then you combined all your like terms. And this function is in red is f minus g of x. And then down here, you took that function and you plugged in 2. So you took 5x squared minus 11x plus 9 and you plugged in 2. And you simplified and evaluated it at 2. Exponents first, then multiplication, finally addition to get 7. All right, so we can also consider adding and subtracting functions, and we're actually creating new functions when we add or subtract those two. Okay, so next what we're going to be doing is we're going to be looking at the graph of quadratic functions. And any quadratic function in variable x, for instance, it's degree 2, so it's going to be of this form, like ax squared plus bx plus c, where a, b, and c are numbers. All right, we're going to do the most basic. We're going to look at f of x equals x squared. And to graph this, we're going to just do an xy table for now. We'll look at more sophisticated ways later. And let's plug in, we'll just go -3 to +3. And we're going to be just squaring all of our inputs, because that's what f of x equals x squared does. It takes our input and it squares it. So first of all, everything's going to be positive, because no matter what the number is, when we square it, it'll be positive. All right, so we're squaring all our x values. And now let's go ahead and graph this, and we'll start defining some vocabulary terms. So, I wish that was straighter, that's okay. We have to go all the way up. We're going from 0 to 9 on the y-axis. 1, 2, 3, 4, 5, 6, 7, 8, 9. And then just -3 to +3 for our x-axis. Let's start plotting our ordered pairs. So -3, 9 is our first ordered pair. -2, 4. -1, 1. 0, 0. 1, 1, 2, 4. 3, 9. All right, and we just happen to stop here, but this would go on indefinitely, and we'd be continuing this pattern. All right, try to make this as smooth as possible. It should be a nice smooth curve. And these arrows, again, they just mean that the x values go on and on and on, and the y values go on and on and on. All right, so essentially, I know it doesn't look like that very much on my big graph, but the shape we're getting should be a smooth curve, something like this. And this curve is called a parabola. And all quadratic functions have this graph of a parabola. So the shape is called a parabola, and we're going to just name some parts of our parabola. Let's go back down to here. In this case, the lowest point was that 0, 0, and it's called the vertex of the parabola. And in this case, it's the lowest point. It's the lowest point. Also, because we're squaring, and all negative and positive numbers, when we square them, become positive, all parabolas are symmetrical. And this one is symmetrical right down the middle. So if we put a mirror on the y-axis, we would create the same shape of our parabola. So this is called the axis of symmetry. Symmetry. And in this case, it's a vertical line, and it happens, it's always going to go, the axis of symmetry always goes through the vertex, and that vertical line is x equals 0. All right, so the axis of symmetry always goes through the vertex. A couple other things we want to mention. Whenever we're looking at the graphs, we like to talk about the domain and range. The domain is all the x values. So are there any x values that we cannot square? We can square all of them. So the domain is all real numbers. If you wanted to use interval notation, you could write that as -infinity to +infinity. Our range is more restricted. Notice when we square a number, we can never get negative numbers, right? And we can even look at our xy table. All of the y values, or all of the function values, are not negative. They're only positive and 0. So our range can never go below the x-axis. We're not going to get any y values down here below our x-axis. So we're going to say that the range is y is greater than or equal to 0. Greater than or equal to 0. Okay, and then final thing, I'm going to talk about the vertex. One more thing about the vertex is we had a parabola that looked like this, looked like a cup. So it was facing up, is a happy face, and sometimes our parabolas can face down. They can be a sad face. So if we remember that the vertex is at this point, sometimes the vertex is the minimum value on our function, When it's a happy face, the vertex is a minimum value. And when it's a sad face, our vertex is the maximum function value. And I should say again, we're talking about the maximum function value. And that's going to be important later on when we're doing word problems. Okay, so final thing that we're going to be doing is we're going to be graphing a cubic function next. Remember, cubic has degree 3, so it's always going to look like this. All cubic functions in one variable are going to look like ax cubed plus bx squared plus cx plus d, where a, b, c, and d are numbers. And the most basic one is x cubed. So a is 1, b is 0, c is 0, d is 0. And we're going to graph this. We're just going to go -2 to 2 in our xy table because cubes get really big very quickly. All right, and then let's see what happens when we take -2 and we cube it. Well, -2 cubed, I'm going to write it out. When we have a negative base and an odd number, we end up with a negative number. An odd exponent, I mean. Likewise, with the -1, we have a negative base, an odd exponent, so we end up with a negative number. 0 cubed is 0, 1 cubed is 1, and 2 cubed is 8. All right. And the reason why I didn't include -3 and +3, well, now we're looking at -27 and 27. That would be really hard to graph. All right, so again, these cubic functions get very big very quickly. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, -8. 1, 2, 3. 1, 2, 3. All right, so let's start graphing our ordered pairs. So -2, -8. -1, -1, 0, 1, 1, 2, 8. All right, and the shape we're getting is something like this. Okay? So let's talk about this function. So no special name for this function, the shape of the function, that is. But let's talk about the domain. Any number exists that we can't take to the third power? We can raise any number to the third power. So the domain is all real numbers. And then look at our table of values. Are we getting negative numbers? Are we getting positive numbers? Are we getting zeros? Yep, we're getting everything. And again, make sure your function has arrows, because again, this means we're going to continue in this pattern. We're going to hit all the x values. We're going to hit all the y values. So our range is also all real numbers. Okay, and then just to comment on the shape of some cubics. So again, this was our very basic cubic function. It looks something like this. Other varieties we could have that same version, but just negative. something like that. And then we can also create the more complicated cubic, so not just x cubed, but if we were to throw in more terms, it could get a lot more bumpy. So maybe something like this, or something like this. These would all be examples of cubic functions. Cubic functions.